So music theory is very much its own language. And when we talk about music theory, there's kind of two distinct languages that we can use. There's one that's kind of more mathematical in nature, where you talk about things like waves and frequencies and ratios. And then there's one that's a little bit more musical in nature, where you talk about things like pitch and octaves and, chord progressions and cadences and things like that. But one of the most important things that you can understand from the very beginning is that these two different languages are actually talking about the exact same phenomena. And musical language is kind of an abstraction on top of the mathematical language. So it's really important when we're starting out to actually understand the underlying physical concepts and how these musical terms actually relate to them. So I'm going to start off the series by talking a little bit about physics, and then we're going to quickly move into the musical notation just so you have a grounding to kind of follow the rest of the videos in this series. Any kind of audible sound is going to travel through the air as a wave that looks something like this. And it doesn't matter what kind of instrument you're playing or anything like that. So if we have a guy over here that's playing a little piano or keyboard, and there's some guy over here that's listening to him, it doesn't matter what instrument he's playing, it's going to emit a wave like this that goes to this guy's ear so that he can hear it. And it's not going to emit a visible wave the way that a video game boss would or something. What's actually going to happen is that there's particles in the air. So there's like individual air particles, and the wave is going to travel through the air, and it's going to displace the particles in its way as it's going. So you could just imagine the particles moving in this kind of wave-like pattern until it reaches this guy's ear. And what's really important about this phenomenon is that regardless of what instrument you're playing or how loud you're playing it or if you're speaking, the wave is always going to travel through the air at the exact same velocity. And velocity is the scientific term for speed, but these are the exact same thing. And the velocity of an audible sound wave through air is going to be fixed at 343 meters per second. This is what you often hear referred to as the speed of sound. And the only way to ever change this velocity would be to change the medium that the wave is traveling through. So if I was playing the piano underwater, this velocity would change. But regardless of what instrument I'm playing, if I'm going through air, the speed's always going to be the same. It's a common misconception to think maybe, well, if I just hit the keyboard harder, maybe it'll go faster. But that's not actually what happens. When you hit a keyboard harder or like play something louder, you're actually changing what's called the amplitude of the wave. So you're changing how tall this wave is. And you can imagine it like this, where it's displacing more air particles, but it's actually traveling still at the exact same velocity through air to this guy's ear. The wave that we were just looking at is a sine wave, but waves can have a lot of different form factors as well. So you can have things like square waves that are very punctuated. They go up almost instantaneously and they sustain their top amplitude for a while. You can have things like sawtooth waves. So those are waves that go up immediately and then gradually descend. These kind of wave form factors don't really occur that often in nature, but they're very common in digital music on synthesizers, and they're used in electronic music a lot. And then you can have waves that are kind of triangular waves. So they look like the sine waves, but they're just a lot more punctuated as opposed to gradual. And despite all these different form factors, they all travel again at that exact same speed of 343 meters per second. And all these different form factors of waves have different sounds. We're not going to worry too much about that. I just want to emphasize one important point. Regardless of the form factor of the wave, you could see that there's always going to be these crests. So a crest is the term for the top of the wave, and there's always going to be a crest, and then there's going to be a distance that happens between each crest of the wave. So this to this to this. And this is something that is called the wavelength of a wave, and this is measured in meters. So each wave has a distinct wavelength to it. And you could also think, because this wave isn't just stationary, it's traveling in a direction, and it's traveling in a direction at a fixed speed, we could draw a point and say, this point right here, we are going to measure how many crests pass by this one point in a second. And that is something that's called a frequency. And this is measured in a unit called hertz, or abbreviated Hz. And hertz is the number of crests of a wave that passed by a fixed point in a second. And again, because the velocity of a wave is fixed, we know that if we change the frequency, so if the frequency increases, that must mean that the wavelength is getting smaller. So if we increase the frequency, we must be decreasing the wavelength because it's going at a fixed speed. So if the waves were closer together, is the only way that the frequency could be going up. And there's a formula that we have where V equals F, which means frequency, and lambda, which is the abbreviation for wavelength. So the velocity or speed of a wave is equal to its frequency times its wavelength. And this is generally true for any kind of wave, but for sound waves in particular, it makes intuitive sense because we know that our velocity is fixed at 343 meters per second. So we know that if we're increasing the frequency, in order for this number to stay fixed, we must be decreasing the wavelength like this. So I'm going to make a statement, which is somewhat of a simplification, but for all intents and purposes, we can think of it as true. When we want to change the sound of a wave, really the only thing that we can change about it is its frequency, because the velocity is fixed. And when we change the frequency, the wavelength changes in congruence with it. So we can think of manipulating the sound of a wave as manipulating its frequency. And the range of human hearing, the frequency that humans can hear in, is a range of 20 hertz to 20,000 hertz. So this is the range of manipulations that we make when we change the sound of individual notes. This brings me to my first major revelation of this series, which is that frequency, which is a term in physics, is equivalent to pitch, which is a term in music. So these two terms are referring to the exact same thing. When you increase the frequency of a wave, which is something that you do in physics, you are increasing the pitch of a note, which is something that you do in music. And this is really important because knowing that frequency and pitch are the exact same thing is the bridge that we're going to have between the musical language over here and the mathematical language over here. And just to show an example of this, I'm going to play a square wave audio signal that has a frequency of 440 hertz. And now I'm going to play the exact same signal with a frequency of 2000 hertz. And you can see that what we perceive as the pitch of the tone has increased along with the frequency. So back before we even knew how to measure wavelengths in the 1700s or whenever that was created, people still made music. They've been making it for hundreds of years, and they figured out that if you could take a string and you could vibrate that string, it would produce a sound wave of a certain quality. And depending on the properties of the string, the frequency and thus the pitch of the sound wave would change. So for example, if you have a thin string versus a thicker string, the thinner string is going to produce a wave at a higher pitch than the thicker string. Likewise, if you have two strings of the same thickness, but one is shorter than the other, the shorter string is going to produce a sound wave of a higher pitch than the longer string. Also, if the tension of two equal strings, so you have two of the same string, but one is wound up tighter and has more tension than the other, the string with more tension is going to produce a higher pitch wave than the one with less tension. And also, the material of the string could matter also. So if you have two strings of identical thickness and identical length and identical tension, and one is made out of copper and one is made out of steel, well, copper is a denser material than steel, so the copper string is going to have a smaller frequency than the steel string, which will have a higher frequency. So people figured out that you could make instruments and manipulate the pitches just by changing the properties of the strings. And early musicians would make a pretty interesting discovery. So let's make a really quick chart that's just an increasing pitch. So musicians noted that you could make a sound, and then you could manipulate the string to make the pitch higher and higher and higher. But what would eventually happen is you would arrive at another sound that sounded extremely similar to a sound that you had made before. Even though the pitch was higher, there was something about the sounds that just, had a common quality, almost as if they were different shades of the same color. And then you could keep increasing the pitch and get different sounds and all kinds of different sounds. And then once again, you would arrive at a sound that had a very similar quality to the previous sounds that you had made. And you could do it again. You could take a sound down here and you could increase the pitch over and over and over. And eventually you'd arrive at another sound up here that was similar to the sound down here. And over again, up to here, you would notice that these three things had a very similar quality to it. And musicians would label these similar sounds with letters. So they could say, like, this sound down here is an A, but then you can get to an A that's a higher pitch, and then another A that's a higher pitch. And then maybe this sound is a B. And then you can get to the B again, and you can get to the B again over here. But there was something similar about these sounds that musicians wanted to categorize them as shades of the same thing, even though the pitches were different. And once we learned how to measure music, or measure waves, there was something really interesting that was discovered, which was that the sounds that early musicians had classified as similar turned out to have 2x the frequency of the lower sound. So, for example, if this sound that had been classified as an A had a frequency of 440 hertz, this other sound that was classified as an A would have a frequency of 880 hertz, meaning the frequency would be exactly 2x the other frequency, and this A up here maybe would be, 1760 hertz. You're probably somewhat familiar with this concept if you've ever heard that song that's like do, re, mi, fa, sol, la, ti, do.
Do, re, mi, fa, sol, la, ti, do.
Where you have a singer singing a note at a lower pitch, do, and then singing an increasing succession of higher pitches, and then arriving back at the exact same note that they started at. Even though they're at a higher pitch, there's something similar about the notes that the two do's are being sung at. So one of the things that we could do is make a bunch of letters that represent pitches on that spectrum and map them out. So A, B, C, D, E, F, G. And this would be 7 different pitches. And then if we wanted to go up to the next pitch, we could 2x the frequencies of all of these pitches and arrive again at a series of pitches A, B, C, D, E, F, G. And then we could 2x all of these things again and have another set of A, B, C, D, E, F, Gs. So these are 7 distinct sounds that we can 2x the frequency on and have another set of those exact same 7 discrete sounds. And this in music is called an octave, right? An octave. So an octave represents a set of all of these letter sounds and then just what range that you're at. So each octave is numbered. So for example, the first octave is octave 0. When you 2x the frequency of everything in octave 0, you get to octave 1. You can 2x that, and then you can end up at octave 2, etc., until you're out of the range of human hearing. Now, what that allows us to do is to create a 2-tuple to represent any musical note. For example, we can say A, which is the class of the sound, and 0, which is the octave. So A0 equals a wave that has the frequency of exactly 27.50 hertz. Now, just knowing that it's an A we don't know which octave it's in, so we couldn't tell you what the hertz are, but if we know that it's A0, we know it's exactly 27.50 hertz. And we know that if we go up an octave, we 2x the frequency, so A1 would be a musical note that has a frequency of 55 hertz. Likewise, we could go along in the same octave up another note, so we could have B0, which is in the same octave, but it's a different note, and B0 would have a frequency of 30.87 hertz. Okay, I hope that makes sense. The next thing I'm going to add to this is going to be a little bit more complicated, which is, well, what happens if I wanted to play a musical note that had a frequency in between where A and B are? So for example, what would happen if I wanted to play a note and I wanted the frequency to be something like 29.14 hertz? Well, if I, was labeling these instead of with letters, but I was labeling them with numbers like 1, 2, 3, 4, it would be kind of obvious what I would call that. I'd call it like 1.5 because it's halfway between 1 and 2. Well, because we're using discrete values, like letters of the alphabet, there's no concept of halfway between A and B. It's just a meaningless term. So we have this term in music called A sharp. And A sharp represents halfway between A and B. So this would be a note just like A, but it's just declaring that it's halfway between A and B. So we'd call this A sharp 0, because A sharp is in an octave just like B, and it's a frequency that's approximately halfway between A and B. And then we could obviously go up an octave with our A sharp also and call this A sharp 1, and then this would be a frequency that is 58.28 hertz. So that's not super complicated. It's just a term. The sharp just means a frequency that's halfway between A and B. Now, I hope that that makes intuitive sense to you, because I'm going to explain 3 things now that are going to make no intuitive sense at all. And these are 3 things about musical notation that are extremely important to wrap your head around, but they might be a little confusing the first time you hear them. And I didn't invent this stuff. I'm just going to explain it to you. It's going to suck, and it's not going to make a lot of sense, but you're just going to need to take this shot of vodka now, and trust me that you just need to wrap your head around what I'm about to tell you. Okay, confusing thing number 1. A lot of times we are going up the scale in an octave. So we're going from A to B. So using the term A sharp makes sense because we're starting on A and then we're going to B. But there were going to be times when we're playing music where we're going down the scale. So we're going from B to A. And in that case, it might make sense to think of this halfway point as something relative to B, not A. So we have this term that you'll probably see a lot, which is like B flat. And this B flat means the exact same thing as A sharp. These 2 things are equal to each other. B flat is the frequency that is halfway between B and A. So it represents the exact same note as A sharp. So there's a B flat 0, there's a B flat 1, etc. So you can, this is really confusing to think, why are there 2 names for the exact same frequency? Like if you're playing a piano, the key A sharp and the key B flat are going to be the exact same key. Now, I told you this is just going to be confusing, and you're just going to need to wrap your head around it. But for all intents and purposes, you can effectively ignore the fact that B flat is even a thing, or any flat is even a thing, and just think of A sharp as the value between A and B, and I will explain flats later in this series. Okay, confusing thing number 2 that you need to wrap your head around. Let's take a look at notes E0 and F0. So E0 is a note that has a frequency of 20.60 hertz. Now, if we look at the distance between A and B, A has a distance of about 3.3 hertz between A0 and B0. And then there's about 1.74 hertz between A0 and A sharp 0. So if we were thinking what the distance between E0 and F0 would be, we would think it would be approximately the same as A0 and B0. But it turns out the value of F0 is 21.83 hertz. So this is a lot more similar to the distance between A and A sharp than it is between A and B. And it turns out that not every letter has the same distance between it. In fact, there can be distances between whole letters that are really half distances. And I know that's insanely confusing. It really is. But sharps are just kind of arbitrary notation to represent frequencies. So, there's no E sharp. This is a concept that doesn't exist in music because the distance between E and F is the same as the distance between A and A sharp. So again, it doesn't really make a lot of intuitive sense, but just know that sharps are arbitrary. They're not like a mathematical property or anything. So it's possible that you can have, letters as categories, and then the distances between them are the same as the distances between a letter and a sharp somewhere else in the scale. And if that's not bad enough, there's a third thing that you need to wrap your head around to understand this notation properly. So we said that A0 has a frequency of 27.5 hertz. B0 has a frequency of 30.87 hertz. C0, what do you think C0's frequency is? It should be something like 33 hertz. That would be my guess, at least. It turns out, though, the frequency of C0 is 16.35 hertz, right? So It turns out C, the letter C, even though it's not the first letter in the alphabet, it actually is the lowest frequency of any octave. So we can think of the octave as a continuous scale upwards, but it just starts at C instead of A. So for example, you could write C, then C sharp, then D sharp, then E, etc. up the scale. So one way that you can think about notes is as the same root frequency. For example, G, which G0 is 24.5 hertz, and it's that same root frequency just extended up octaves. So these have similar sounds to each other, but you're just playing it higher and higher pitches, and that would be one way to think about it. So another way to think about notes are the series of notes that are available in any one given octave. And it's a range that goes from C to B, and there's exactly 12 notes. There's 7 letter notes, and then there's 5 sharps. Note that there's no sharp between E and F, and then there's no sharp between B and C. So that's how you get 12, 7 letters, 5 sharps. Now what's really interesting is that there's 12 notes in an octave, and then there's about 10 octaves in the range of human hearing. So that means there's really only 120 notes that are ever played in Western music. So any song that you've ever heard probably uses the same 120 notes in different combinations. That's why when you listen to something like Indian music, it sounds really different, where they have that ah, where they have like the quarter intervals between different notes that just don't exist in Western music. But anyway, these 12 notes in one octave is something that is called the chromatic scale. And the chromatic scale is what we are going to talk about in the next video.